Okay, everyone. This is Braden 10, and today I'll be reviewing molecular orbital theory. So let's get started. To start off, the question really is, what is molecular orbital theory? And so it's a bonding theory that was formulated by Robert Mulligan based on quantum mechanics. It creates similar atomic orbitals, and so similar is like in shape or energy, to create molecular orbitals. So the molecular orbitals are areas where the electrons in a molecule are located and are shared by all the atoms within a molecule. Kind of see that as we go on. But for me, what I actually look at first is the benefits and disadvantages of molecular orbital theory, especially since this follows valence bond theory, and knowing both is really useful in knowing, the advantages and disadvantages that each have. And so some of the benefits of molecular orbital theory is that you can predict the bond energy, even though it is pretty difficult, and you're not going to be able to do it just with the materials we have right now, but you can still do it. Um, you can use it to predict bond order. You can also use it to determine magnetic properties and to determine absorption and emission spectra. And then a disadvantage is that you can't predict molecular or electron geometry, but that's okay because you can do that using valence bond theory and VSEPR. But it's the way I kind of designed this. I want to just go ahead and get into all the benefits and how we can understand those and use those. So, but first, it's important to understand really what are molecular orbitals. So there are two types of molecular orbitals. So there's bonding orbitals, which are electron-dense areas in molecules that increase electron density and hold the atoms together. And so these tend to have, well, these do have lower energy than antibonding orbitals. And going off that, antibonding orbitals are areas of electron density that do not increase the overall electron density. And so the fact that it doesn't increase them, it destabilizes the molecule, which is why they're anti-bonding. And these orbitals have higher energy than bonding orbitals. So this next slide, I'm going to show you just really exactly what they are, so it makes a lot more sense. But here's an energy diagram. Didn't include it on here, but you can just, the trend as it goes up is energy, and energy level increases as you move up. But so this is a molecular orbital diagram, energy diagram. I've just labeled all the parts so we can understand that here. But you have your atomic orbitals. That's in this example, it's 2s, 2p is the ones we're familiar with, but they can be different, like a 5s, 5p. And then you have your bonding orbitals. And I just put in the parentheses. Notice that you have a sigma and a pi. And these are the same terms we use in valence bond theory, but just remember they're not bonds, they're orbitals. And then you have antibonding orbitals. As you can tell, the energy increases as you go up, so they're above bonding orbitals, so they're higher energy. And same with this one, it's higher than that. And when looking at one of these diagrams, the way that you can tell the difference is, it's pretty clear. Antibonding orbitals have this little star by them, and bonding orbitals don't. And while we are looking at this, I just want to go over two terms that are used. So the first term is HOMO and the second is LUMO. And so HOMO stands for the highest occupied molecular orbital, while LUMO stands for the lowest unoccupied molecular orbital. And while this is just an empty diagram, say this was filled, let's just say there was 2 electrons here, 2 electrons here. So your HOMO, the highest occupied molecular orbital, I think it's pretty self-explanatory. This is a molecular orbital, and if it has 2 electrons, it's occupied. And if let's say there's nothing here in this pi orbitals, That means this sigma star would be the HOMO, the highest occupied molecular orbital, because there would be 2 electrons in it. And then the LUMO would just be this pi right next to it, because it's the lowest unoccupied molecular orbital. So I guess it can be kind of confusing because you have highest, which is actually lower, and then lowest, which is actually higher. But the key is really the occupied and non-occupied. And if you get that down, I do think it's pretty simple and easy to understand. But now that we just kind of understand and know how the diagrams work, let's go on. So the first thing I talked about in the advantages is well, I don't remember exactly, but I'm just gonna go over all of them anyways. This is predicting bond order, or how to predict the bond order. And so using the antibonding and bonding orbitals, we get the formula of the number of bonding orbitals you have minus the number of antibonding orbitals divided by 2 gives you the bond order. So the example here, you can just see it's 8 bonding orbitals minus 4 antibonding orbitals divided by 2 is a bond order of 2. But let's just go over this picture so you can see it visually. So your bonding orbitals, check to make sure, this is a little blurry, but just to make sure it doesn't have a star. So you have 1, 2, 3. These 3 levels are filled. So you have 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 bonding orbitals. You notice this sigma has a star and this pi has a star. That's 1, 2, 3, 4. So it's 8 minus 4 divided by 2 gives you a bond order of 2. That's another one I think is, it's fairly simple and just a little bit of practice, and that should be something fairly easy to do. Just a note, I put this little asterisk here. If the bond order is 0, then there's actually no bond. So the example we had in class is that of diatomic helium. And so this really isn't it, but just imagine it is. Just cut off this whole top part and imagine you just had this bottom, these bottom 2. And so that would have 1, 2 bonding orbitals and 1, 2 anti-bonding orbitals. So 2 minus 2 is 0 divided by 2 is 0. And so, I guess you can calculate that, but since it's 0, there's no net change, and so there's actually not a bond. So you're not going to be able to really find that anywhere. Just a note, something to recognize. But I put a few examples on here so we can go ahead and go into that. But I can just give you a second or two to pause the video if you want to calculate these, and I'll do them anyways after. Okay, so hopefully you did that. If not, that's okay. I'll do it now. But let's look at the diagram. Let's identify bonding and the anti-bonding. So here we have a sigma, and pi. And whoops, sorry. Let me go back here real quick. So you have bonding, bonding, bonding. And then the anti-bonding are the ones with the stars. And so let's just count here. We have 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 minus 1, 2, 3, 4. 8 minus 4 divided by 2 is 2. So just like the last one, the bond order on this one is 2. So let me go ahead, move on to another example. So this one might seem a little more difficult, but that's just because they went into a little more depth explaining, what the atomic orbitals are and how it forms. But, principle's the same. So here's your bonding, 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 anti-bonding, anti-bonding. So 1, 2, 3, 4, 5, 6, 7, 8 minus 1, 2, 3, 4, 5, 6. So 8 minus 6 is 2 divided by 2 is 1. So this has a bond order of 1. So yeah, those are some examples. Like you can probably tell they're pretty straightforward once you figure out what the diagram looks like. But let me go on. So how can you recognize, what's a sigma bond and what's a pi bond? And sorry, what's a sigma or pi orbital? And then, which ones are bonding or anti-bonding? The way I like to look at it is that your sigma bonding orbitals have a plane running through the two nuclei that are lined up. And so let's just look at this picture. So these are your atomic orbitals, but this is a sigma 1s bonding. So you have the two nuclei next to each other, and I just see this vertical plane running through it uninterrupted. And then, for pi orbitals, they the plane doesn't, or I don't know how to explain it well. So there's a gap where, versus in sigma where you could have a plane running through it, there's a gap where that should be. So you can just look at this pi bonding orbital. See, there's a gap right here whereas in sigma it's connected, in pi it's not. And then anti-bonding orbitals, determining them versus a bonding orbitals is also pretty straightforward, I'd say. You just look for this vertical node, vertical gap. And so you can tell this one, it's still the sigma antibonding, you still have a plane going through that touches both of them, but there's this big vertical gap. And then, it's kind of the same with this these pi antibonding. There's still that horizontal gap that sigma bonds, sigma orbitals don't have, and then also has this vertical node that separates that as well. So you can tell it's just this one with a slice in half with that vertical node / gap, whatever you want to say it. But just recognizing that helps me a lot, and I feel like most of you do that as well. That's how you recognize and can tell what is what. Let's go ahead and keep going. So here are some more examples. So I can just give you a minute to sit and think this over and try and figure out which one this is. And I'll tell you later. Okay, hopefully you figure that out. This is pretty straightforward. Even it looks kind of not like the other ones we looked at. Is there a vertical node separating it? No, so it's a bonding orbital. And then can I draw this plane through the two nuclei without, this horizontal gap forming? And yes, I can. So since I can draw the plane through, it's sigma, and since there's no gap vertically, it's a bonding orbital. So this is sigma bonding. Sorry. Yeah, sigma bonding orbital. Let's keep going. So this is a little blurry, but yeah, I'll give you a few seconds again to just sit and figure this one out. Okay, so go ahead and tell you this one, explain this one. So this one you see pretty clearly, this vertical node gap thing. And so that tells us it's anti-bonding. And notice how it kind of like pinches, it's rounded out. I mean, they look together here, but you know that just from the shape, this is the gap. So the plane runs through, and the nuclei aren't located within this plane. And so that lets you know that this is a pi molecular orbital, and it's anti-bonding since it has this vertical node perpendicular, however you want to say it, and the two nuclei aren't lined up on a horizontal plane. I'm just going to keep on going. And so what else can you learn from these diagrams? So some of the other things you can read from a molecular orbital diagram or is the magnetic behavior. And so molecules are either paramagnetic or diamagnetic. And paramagnetic means if there's any lone electrons at all in the diagram, it's paramagnetic. And if all the electrons are paired, it's diamagnetic. You might get confused, paired, paramagnetic, which isn't right. But the way I see it is just, they're all paired. Pair is two, di means two. So like diamagnetic means two. And so that's a pretty easy way to see it. Here's some examples right here. So I have this this anion, and it's paramagnetic. So let's just look at this. So you have your electrons here filling it up. And notice that this one in the sigma antibonding is all alone. So it's a lone electron. So that automatically tells us that it's paramagnetic. And then here's an example of one that's diamagnetic. That's the cyanide. And so all these orbitals are filled up, and this highest one, the HOMO, highest occupied molecular orbital right here, it's paired, so everything else is paired, and so you know that it's diamagnetic. Hopefully that makes sense. And one thing I actually neglected to tell you guys before we move on is the way that these are filled up with electrons, and it's just it follows all the same rules that your atomic orbitals follow. So let's say we're going back to this anion. You start here, so you fill up this 1, 2, and then on these pi molecular orbitals where they have two spots to fill, you don't go 1, 2. You don't put 2 here. You go 1, 2, 3, 4, and then you can move up 1, 2, 3, 4, 1. Yeah, so this one would have filled up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so sorry I forgot to say that earlier, but pretty important, so I didn't want to forget that. And that's just how you can fill these in after you figure out how many electrons go in there, which is determined by the valence electrons of whatever is being bonded. So let's move on. So yeah, here's some examples. I'm just going to use the same ones from the bond order because, it's helpful. So I'll give you just a few seconds to see if you can figure this out. Okay, so here, the first thing we'll look for is the HOMO, the highest occupied molecular orbital. So that's right here. And so, you have 2 here. You might be tricked into thinking that, oh yeah, well, there's 2, that's paired. But remember, it goes 1, 2, 3, 4. So there's actually 2 unpaired electrons. So this one is paramagnetic. For the other example, just give you a few seconds. Okay, hopefully you figured that one out pretty easily. But again, go to the highest occupied molecular orbital. That's right here. So you have 1, 2, 3, 4. So everything else is completely filled in. These are filled and paired up. So this is diamagnetic. So, yeah, so anything else? What else can you get from this? And so you can determine emission and absorption spectrum looking at a molecular orbital diagram. And so as you know, your electrons, they can jump up or go down a level. What we remember from emission, absorption, it depends on whether you absorb or emit a photon, sorry. And so you see here, when an electron jumps up a level, they're absorbing a photon. And when they relax to a lower level, when I say level, I mean a molecular orbital level. Here to show you. So these are just levels. So let's say like one of these jumped up there versus and then going back down. So when it relaxes to a lower molecular orbital level, the electron emits a photon. So that's also pretty basic. Hopefully that makes sense here. That is it. I'm sure I covered everything. Hopefully that helped. I just kind of went over all the things that really make sense and it helped me. So I hope that this is something you can understand well and do well on. And that's really all I have. And so thanks for listening and have a good one.